First, want to thank Scholastic for making their wonderful auditorium available to us again, and thank the New York State Council on the Arts, contributors to the League's annual fund, and League members for the support that makes programs like this one possible. Tonight's event is the first in the series From Field to Form that looks at natural materials and their potential to make possible not only a more deeply environmentally conscious and benign architecture, but also new ways of conceiving architectural form. That we need intensive research and invention in this arena is increasingly evident for all kinds of reasons. At this point, year by year, if not month by month, we're ever more technologically capable of reducing the role of fossil fuels and thus climate change impacts in the operation of buildings. That, of course, changes the relative importance of embodied energy in the overall calculus of building impacts. The greenhouse gas generating inputs that go into the production and transportation of building materials become ever more important. There are other reasons, though, as well, to be much more attentive to the composition, provenance, and multiple environmental impacts of materials. Material choices have consequences. The complex life histories of materials need to be followed back to the impacts on the workers and ecosystems involved in their production, the impacts of their transport and distribution, their effects on building users, and their life as waste products after building demolition. Research, invention, experimentation, and not infrequently the rediscovery of earlier ways of doing things to find better approaches to material choices is crucial to make construction less energy intensive and healthier. That general thinking about the critical importance of deeper understanding of materials is the overall impetus for this series, with the immediate catalyst being a remarkable book recently published by LTL Architects called The Manual of Biogenic House Sections that examines the characteristics of natural materials and their deployment in a group of fascinating house projects from around the world. Tonight's program is structured around some of the arguments made in that book, followed by brief previews of the opportunities and state of play in research and deployment of specific natural materials. Subsequent programs in this series will examine these specific materials in greater depth. And here I want to put in a plug for the second program in the series, which will take place on March 15th and will be on structural stone, and that will be at ABC Stone in Greenpoint. So for tonight, Mark Suramaki, David Lewis, and Paul Lewis, the founders and principals of LTL Architects and authors of Manual of Biogenic House Sections, Materials, and Carbon, will begin the program with an overview of their arguments in the book. In addition to his role at LTL, Paul is professor of architecture at Princeton University School of Architecture and immediate past president of the Architectural League. Mark Suramaki is a member of the adjunct faculty at Columbia's GSAP and president of Storefront for Art and Architecture. David Lewis is dean of the School of Constructed Environments and professor of architecture at Parsons. Their presentation will be followed by presentations by Lola Benalon, Mei-Ling Loco, and Jansara Ruth, all of whom are doing important research and teaching on natural materials. Lola will talk on construction with earth and materials. She directs the Natural Materials Lab and the Building Tech curriculum at Columbia GSAP, where she's an assistant professor of architecture. Mei-Ling Loco is an architectural scientist, designer, and educator from Ghana and the Philippines who works with agro-waste and renewable bio-based materials. Mei-Ling teaches at the Yale School of Architecture and previously served as director of the Building Sciences program at RPI. Jansara Ruth, who will talk about hemp and lime, is a designer, artist, and design director at the Healthy Materials Lab at Parsons School of Design. In addition to her work at Parsons, Jansara leads Salty Labs, a collaborative design studio founded in sustainable thinking and testing experimental methodologies. All 6 presenters will come together for a discussion following the presentations, and then we'll have time for audience questions, so get your questions ready. Now, please join me in welcoming Mark Suramaki.
Thank you, Rosalie, and thank you all for coming tonight. As Rosalie outlined, we're going to start tonight by providing a kind of brief framework, a kind of overview of plant and earth-based materials, biogenic and geogenic materials, their kind of urgency, their implications for architectural form, and their relationship to material life cycles. And so to start with really this question of why is it that we need to think and talk about a shift in our material economies. This is a graph probably not unlike other graphs that you've seen that relates the kind of global greenhouse gas emissions to planetary warming scenarios that in this case shows our kind of current trajectories. And this, on the other hand, shows where we actually kind of need to be. If we want to have a high probability of meeting the 1.5 degree centigrade limit established by the IPCC, that will hopefully allow us to avoid some of the most catastrophic impacts of global climate change. So you see this is a radical reduction, 65% reduction in global emissions in carbon by 2030, and essentially global net zero by mid-century. If we look at the amount of carbon related to buildings, essentially it's 39% of global carbon emissions that could be subdivided into operational carbon. In other words, the carbon associated with the energy needed to heat, cool, and otherwise operate our buildings at 28%. And then embodied carbon, which is really what we're going to be talking about primarily tonight. Which is really the carbon associated with building materials and construction. In other words, embodied carbon is the physical matter of architecture. Now that 11% may not seem terribly substantial, but if we look at this relative to the very tight timeframes that are required, again, to kind of avoid the sort of predicament that we're in, the percentage of embodied carbon moves to about half of the total carbon emissions that will be associated with new construction across the world in this very sort of critical time period of the next 30 years. And if we think about the influence or impact of more energy efficient buildings and highly thermally performative buildings, the importance of that embodied carbon increases. It'll be about 56% of the embodied carbon in that context. So the other kind of critical thing about embodied carbon is that it's upfront carbon. In other words, it's carbon that's already expended at the moment that the building is constructed. So it's already emitted or sequestered, whereas operational carbon accrues gradually over the lifespan of the building, placing even more critical importance on embodied carbon as a means to address the kind of global challenges relative to climate change. The other kind of aspect of this, if we look at the next 30 years or so, in that same time frame, the predictions are that the world, across the world, will be adding roughly 2.5 trillion square feet of new buildings, square footage. That's roughly doubling the global building stock in the course of the next 35 years, much of it in the global south. So whereas building less and reuse are really critical ways to think about reducing embodied carbon in the built environment, essentially this means we're not really going to reuse our way out of this situation, just given the kind of incredible demand for new construction. So what does this mean? It ultimately means that we need to rapidly and radically rethink the material preconditions of our architecture. We need to rethink the ways in which we build and what we build with. This also means we need to reassess the legacy of modernism as it's been globally disseminated and its reliance upon carbon, steel, and glass, which are not only three of the most carbon-intensive materials, but also participate in cycles of linear extraction that have devastating impacts on environments and inequitably distributed effects on human health. It also places the architect as a kind of consumer, as a consumer of building products that are assembled into architectural form. By contrast, biogenic and geogenic materials require minimal carbon related to their minimal processing, and in the case of plant-based materials, literally sequester carbon within their very cell structure, allowing for the possibility for architects to reconceive their role as part of larger material cycles of flows of energy and matter within the environment that can actually have kind of positive benefits relative to regenerative cycles. And if we look at the kind of carbon implications of this, we realize that one of the kind of benefits of this, one of the kind of moments of good news in all of this, is that these materials are already here. In other words, they're readily available, they're globally distributed, they're widely accessible, and often are the byproducts of other systems, agriculture, for example. And by and large, we already know how to build with them. So they're inexpensive and plentiful, and they also offer up kind of we think kind of really amazing opportunities for rethinking the architectural basis of many forms of construction, but in the case of the Manual of Biogenic House sections, the publication that Rosalie is mentioning, we examine this relative to specifically the impacts and use of these materials to develop innovative architectures in the form of 55 houses culled from around the world. And this leads to another question, of course, which is why are we talking about houses? What's the relevance of the house? It's part of the problem, arguably. We should be building less single-family houses. But in fact, the house, precisely because of its scale and its ubiquity, offers a kind of fertile proving ground for new material economies and for rethinking the ways in which we build. And if we kind of look at the impacts of roughly 1 million homes built annually in North America, shifting the ways in which we think about the material conditions of houses can have kind of correspondingly substantial impact on the built environment relative to climate. But the way houses are built now is highly problematic. They've essentially more than doubled in size over the course of the last 75 years, and they're filled with toxic materials from heavy metals and gypsum board to PVC in vinyl tiles. These materials are essentially predominantly the byproducts of the petroleum industry. They participate in take, make, and trash cycles, which are non-renewable and ultimately mean that most of these materials end up at the end of life as demolition waste and landfills. If we look at the composition of the wall, we start to realize why this is the case. Kind of contemporary walls are constructed of multiple layers of lightweight, thin, single-performing monofunctional membranes that presuppose a strict binary, a strict separation between interior and exterior. These are also extremely difficult to pull apart and repurpose or to reuse in any way. Biogenic materials often exhibit precisely the opposite characteristics. So houses built with plant and earth-based materials frequently exhibit characteristics of extreme thickness, opening up the possibilities for a revitalized relationship between architects and questions of mass. They often exhibit a reduction of the number of material systems involved and tend towards the monolithic. So frequently in these buildings, a single material performs as structure, as skin, as thermal insulation, and as enclosure. And these houses that we investigated also exhibit a wide variety of approaches to questions of interior and exteriority, gradients of relationships between inside and out, and nuanced relationships between the materials in use and questions of wear and transformation and entropy over time. The book itself is organized according to 9 chapters that correspond to 9 different material systems as well as reuse. And in each instance, we look at the carbon sequestering potential of the material and importantly, its relationship to life cycle, right? In other words, this question of how do we go from the seedling to the plant to the building component to the house, back again through hopefully recycling and repurposing or back into the environment in harmless or regenerative ways. So this is essentially the question of field to form, and it repositions the architecture not as a static artifact, but essentially as a temporary accumulation of materials that are part of a much larger kind of circular logic that can be kind of utilized to generate a transformed relationship between architecture and the natural world. We also look at processing. So how does the tree transform into the truss, as it were? How do we actually look at the maintenance and care of natural ecosystems? And how do these kind of processing conditions in terms of their intensity contribute to the embodied carbon or carbon sequestration of the material? And finally, we look through a series of axonometric drawings, photographs, and cross-sectional perspectives that were generated for the book at the architectural implications of these materials. So in other words, not only how do these houses simply substitute better materials for worse ones, but in fact, how do they actually use an engagement with biogenic or geogenic materials as a catalyst for new spatial and tectonic configurations, for thinking of new imaginative engagements, architectural responses to dwelling in the 21st century?
So the project took 4 years of curating and collecting houses from around the world. And in that process, we also became curious as architects, how could we design from them as well? So we developed 5 biogenic houses, all based upon plant-based, to explore the architectural implications through the question of feel to form. Each of these tended to look at not one material, but actually combinations of materials. In addition to that, we were interested in figuring out how that cross-weaves to the research we were already doing. So what I'll present and Paul will present is the material chapters, weaving together both the material from the biogenic house section book, but is also from our own design speculations on form. First one is mass timber. Mass timber is in many ways the poster child today for plant-based buildings, because it easily seems to substitute for concrete and steel. But it has some challenges. Namely, it takes 30 to 100 years to grow, and in that process, even with certification processes, you have carbon loss in the removal of the tree and the disruption in the carbon in the soil, significantly offsetting some of the carbon sequestration benefits of mass timber. You have in the mass timber the accumulation of different pieces, which also implies glues and their ability to be disassembled. That's why we're actually keenly interested in dowel-laminated timber, because of its capacity to only use wood and not use glue. The other is to pursue, ways of thinking that isn't just a substitution for steel and concrete, but really exploring the capacity for mass timber to generate form. And so in this project by Jennifer Bonner, which is called House Gables, is really an exploration of the tectonic use of the CLT plank to produce a kind of excess of gable forms within the very shaping of the house itself. Or in this one, where you're basically using not just one, but 2 skins of cross-laminated timber to produce an enigmatic figure that also simultaneously produces a thick insulative airspace between these 2 layers. One of the beauties of this house is that it really just uses timber with only a stain on the outside, essentially sequestering through the use of wood roughly 48 metric tons of CO2. In our own project, we looked at essentially how to really continue the exploration of how the CLT blank, or the produced panel, in combination of wood insulation, wood fiber insulation, and wood siding, to produce an only all wood project. Right? And in doing so, we were intrigued by that blank and the capacity for its length or its tallness to produce the architectural form. And these are the diagrams for the house designs, and they're intentionally circular, intentionally reflecting the idea of moving from a field condition to form and then back again. In this case, the assembly is to minimally tool the CLT planks, tipping them up from the back, producing a vertical structure that houses the staircase and circulation in the back, and then as it moves to the front, becoming closer and closer, becoming essentially the A-frame form. What this produces then not only is a vertical structure, but the capacity to be up high in the trees, occupying the space in between the planks, and then within the building, seeing the nested cantilevered volumes for living and sleeping, all within a structure that doesn't have to have additional interior layers or additional exterior layers. Bamboo is another material that, while CLT is maybe limited by the slow growth, bamboo is not. It is one of the fastest growing plant materials. It's prolific. It has a higher rate of carbon sequestration than wood. It can exceed 30 feet in 3 to 5 years, and it's harvested not by clear cutting, but by thinning, giving the rhizomatic nature of the root system. It can be cut into pieces, glued together, produce different forms. It can also just the culms or the stalks itself can be cut and used. Even though they have variation, which challenges some of the kind of logic of standardization, it actually produces intriguing structural unit to be bundled and assembled. And so one of the houses we chose out of Ecuador uses clusters of locally or indigenous culms, bamboo culms, as the structural frame, organizing them into intersecting ramp systems, such that the entire house is defined by the ramps and voids within the inclined surface, animating, in fact, the site itself. Used in very different purposes, here for Anna Heringer's housing or hostel prototype, a weaving of bamboo forms provides a kind of light lattice, a sort of delight, an unprecedented external skin, providing a kind of protective environment on the earth-based condition on the inside for the sleeping and the core, essentially juxtaposing solidity and the lightness within one project. This leads to the next material, earth. Although it does lack some of the ability to work in tension, like bamboo or wood, earth has the capacity to be load-bearing structure. It's also one of the oldest building materials, and one of the things that we should foreground is that this is not a new concept in many ways. It's really trying to reclaim some of the traditional ways of thinking, but now doing it with a lens to the future. It is an older building material, it's ubiquitous, it's inexpensive, it's inherently local, but it's also thickness works as a thermal mass and it can absorb and balance humidity. With clay as a binder, its carbon emissions can be relatively low. A lot of rammed earth, though, is often dependent upon high levels of Portland cement, effectively rendering it as a concrete. And so it's better to use lime or clay as the binder material. It moves from a liquid to a solid state, can be formed as blocks. It's very versatile and can be 3D printed. In the Wohnhaus Fleury, as an example, the loam or the earth was combined with straw to form 32-inch thick, solid L-shaped cob walls, simply cut with a spade. Right? Revealing an incredible juxtaposition on the inside between the wood as this crisp geometry and the wall itself, the ornamentation being the earth from the site. Detailing has to take into consideration its performance, in this case overhangs, to make sure that erosion doesn't occur. One of the fantastic conditions of this is its capacity to be mass, one wall, one material, as insulating, cladding, interior finish, all as one. And in this case, the structural loading is wood, and the straw and wood horizontal members increase its embodied carbon to 53.3 metric tons of CO2e. In this project, 15,000 loam bricks, 4 by 8 by 16 inch, make the walls as well as the ceiling, vaulted ceiling. It's also a way of engaging local labor and skill. A very lightweight use of metal channels water, collects water, and organizes while at the same time providing protection. Most 3D printing you may have heard about is using Portland cement or concrete. And one of the things that this company did outside of Bologna was to use earth itself and to print it in small half-inch layers over 200 hours to produce essentially a building system that through its cavities, multiple layers, is 30 inches thick and can be filled with rice husk for insulation, essentially producing a kind of mass product off of a local condition. In our own proposal, called the Lamella Earth House, we wanted to combine the efficiencies and strength of bamboo, the insulation of thatch or reed on the outside, with interior living quarters made from the earth itself. The lamella structure is essentially a structural canopy of self-similar parts with a same joint. In this case, 8-foot-long bamboo parts all joined together to produce a really efficient, really easy to assemble structure that extends and produces a long-spanning economic system. Right? Thatch insulates on the north side. On the translucent plant-based polycarbonate allows for thermal gain from the south, essentially producing a passively conditioned insulative space within which is lodged the dwelling, which is lodged not only in the earth but native to the earth itself of the site. Essentially what you get is a 30-foot by 292-foot long barn-like space, part greenhouse, part interior, part exterior, for a conditioned way of living on a site, essentially a different model of working, a farmhouse from field to form. So the next three materials we're going to present are all primarily insulation, which is in some ways one of the more overlooked aspects of a building. But on the other hand, it's also a major site of carbon emissions, in part because some of the more common insulative materials are petroleum-based. So hemp itself is a fantastic material. It can be compressed into lumber, but more often it's used as insulation and for the mass of the wall. It grows extremely quickly, about 1 foot per week sometimes, reaching maturity in about 3 months. It has a long root system, aids in stabilizing and regenerating the soil, and it can be grown with minimal water, fertilizer, and pesticides. It should be said that industrialized hemp, which is used for architectural purposes, is different than those grown for the psychoactive drug THC, but their association has led to the disappearance, in a sense, of hemp from the 20th century due to the war on drugs. The fibrous stalk is used for paper, textiles, and it's separated from the hurd by the use of decorticators. The hurd itself is combined with lime and water, produces hemp line, which is sometimes inappropriately called hempcrete, which is durable, fire-resistant, rot-resistant, humidity-absorbing, acoustically beneficial, and an insulating material. But it is not a replacement for concrete. It can be used inside a wall by kind of either spraying it in or compacting, or it can be made off-site in prefabricated panels or formed into blocks. And I'm looking forward to John Sara, who will present much more detail about this fantastic material. Cork is also an amazing material. It's multi-purpose and it's extraordinary in many respects. The downside to cork is there's a limited quantity and it takes a long time to grow, and it only grows in certain regions. So it gets harvested from the bark of cork oak tree about every 9 to 14 years, but it's water resistant, provides thermal, antifungal, acoustic, sensory. If you love the smell of cork, you'll love a cork building, and it also can have structural capacities. But most cork oak is concentrated in the Iberian Peninsula, and the cork in building products is often derived from the excesses of the wine bottle stopper industry. But in this kind of fantastic project that we're looking at here, almost the entire building was built from just cork. It's a monolithic material that is the structure, it's the interior finish, it's the exterior, it's the insulation. There are 1,268 CNC milled blocks that are interlocked into 5 different corbelled roofs that enable the blocks, in a sense, to enclose the space. And again, the downside with cork is really there's just not enough of it, and it grows too slowly in too few places. On the other hand, straw is everywhere. It's ubiquitous around the world. It's a waste product from agriculture. To grow straw does not displace any other food source. It's already there, and it's often left to decompose and let the carbon back into the atmosphere. So the question is, how can we actually delay that and to embed the straw within the building? It grows fast. It's cheap, plentiful, it's resistant to rot, and can be used as everything from insulation, where in a sense the air voids within the straw work to produce the insulative capacity, but it also, if sufficiently compressed, can also be a load-bearing structure. So there are 2 key processes that enable straw to be a viable building material. One is that binding, that kind of compressing, often done through baling on the field. So they're highly compressed into units already. And the second is the plastering of the surface with clay or lime to form resistance to fire, rot, moisture, vermin, et cetera, and also increase the capacity to resist vertical loads. The most common types are what's referred to as the Nebraska load bearing, basically stacking the blocks up. And this refers to the origin of this type of construction in the late 1800s when there was a lack of trees, so buildings were built from straw bales in the plains of Nebraska. It can also be used in filling an existing structural wood frame, using the straw as insulation and also the support for wall surface. It can also be built into prefabricated panels, and in some cases compressing the straw even more, which increases its capacity to resist fire.
thatch roof associated with straw is slightly different, uses a different reed, and is harvested into bundles and would be the subject of a different talk. Anyways, one kind of fantastic example that we were extremely excited by is Atelier Smith's Gardas Pavilion, which uses jumbo bales. These are 30 inches by 50 inches by 100 inches. They're about 650 pounds each. And they were used in this particular project as a load-bearing wall and also corbelled then into the ceiling. So it's a super thick insulating and structural blanket. It contains about 75 metric tons of agricultural waste. And in a sense, that also sequesters about 83 or 84,000 kilograms of CO2 equivalent. So we, in the last two projects we'll present, we were very excited by the possibility of not just using straw, but taking advantage of this idea of, or the possibility of thickness as a catalyst for rethinking domestic space. So with the straw bale house, a straw bale spiral house, we effectively thought about how we could join two different slightly contrasting materials, CLT and straw, with a space of the CLT, in a sense, carving voids within the mass or out of the mass of straw. In a sense, this very small house is defined by a kind of donut or a hole that exists in the middle of a kind of stack of jumbo bales, which measure 4 bales of length in each direction and 12 bales high, about 200 bales. Small prefabricated CLT modules, really open tubes that are placed within and around the bales, stabilize the bales, and also then form the interior of most of the rooms of the house. A CLT stress skin cantilevers, a CLT stress skin roof cantilevers over all sides of the house, in a sense protecting the straw's clay plaster from erosion. And a central skylight continues that central void and allows light to come in from above. The spiral of CLT boxes forms the primary program of the house, which are linked into a continuous spiral moving from the front door to a roof terrace. In a sense, the CLT effectively skins the interior of the straw, erodes or takes away space from the straw. On the other hand, the straw insulates and then reciprocally supports the CLT. As each of these CLT units is open to the two sides, the interior space is all connected through the thick wall to the exterior. The house is both porous and thick. The last project, entitled Mass Straw House, we wanted to find a way that we could make a house that was actually more mass than actually inhabitable space, to sequester as much carbon as possible, use as much straws as we thought was appropriate. So the house is formed really by two different stacks of jumbo bales. One is a long wall perpendicular to the slope of the site, whereas the other is a stack of straw bales which form a kind of terrace form. And these two are connected by a timber box beam that essentially anchors these two structures to each other and provides a substrate for a roof of clay plaster and an additional layer of hemp fiber panels. Furthermore, we kind of laid unprotected straw on top of these layers to, in a sense, decompose back into the site. I think one of the anxieties about straw in particular is that somehow it's going to be the source of animals, and we said maybe that's okay. We could actually allow the mass of the house to decompose into the site. So the main space of the house is between these two assemblies of straw, with the private space of the bathroom and the bedrooms burrowed, in a sense, into the excess mass of the straw, with the surface of the straw in the central space lined with cork. So we end up having a kind of stepped interior landscape for the small house with access to the bedrooms and the bathroom from the stepped collective surface. So here in these two projects, and in this project in particular, thickness, which is in modernist kind of idiom, is conceived almost in a kind of negative term. It's indicative of a lack of material optimization, and therefore it's inefficient. Here we're exploiting it both for its peculiar spatial qualities, while the excess use of agricultural residue results in significant sequestration of carbon. So We believe that there is an important kind of transformation of the material basis of our built environment that has to happen, which also expands the role of the architect to, in a sense, embrace the full cycles of materials from field to form, and also to kind of optimistically embrace these productive potentials. So please welcome Lola Banalan, who brings years of experience in creative engagement to natural materials, in particular to the role of earth-based materials. Thank you.
Here we go. Hello, everyone, and thank you for coming. So I'm going to talk about Earth, but first I want to start and remind us or defy the notion of soil as barren or steel, because soil or geomaterials, thank you for that, are very much also bio. They are full of life and interactions between the minerals, the particles, the fungi, the bacteria, the small organisms. So earth materials that we are, keep thinking about the land, territory as imaginary borderlines, are actually a variance of particle size and webs of interactions. But what do I actually mean when I say earth or earth and construction? Because everything that we call a material in architecture comes from earth, doesn't it? All buildings are geological before they become architectural. So the geological trade routes of buildings dictate their earthly origins. They use strata, rocks, metals, materials, minerals, chemicals, and so forth. So in that sense, couldn't we classify all buildings as quote unquote earthen? Well, not exactly, you know. There are energy transformations that we need to account for that require substances that are more concentrated than their environment to go through chemical, thermal, and energetic work that is needed to create materials that what we call processed, right, that are less natural in a sense. So earth and materials use raw, unfired clay-rich soil as their base binder, fibers as the tensile strength provider, and aggregate as a compression strength provider, allowing for a range of thermal possibilities, geometrical variations, using these non-toxic, community-engaging systems that are easy to learn. And a lot of the work with earth materials is about finding the mix design, the right mix, characterizing and testing the rheological, thermal, structural, and durability properties of the material. And this is an example where we obtained different fiber content mixtures to create a lightweight, radiant, heated structure, in this case, a small-scale chase we call jandag, or body in Aramaic, part of a series called Grounded Chairs that was all about thermal, heated, sculptural sitting. This chase had a radiant heat vanes that pumped heat and energy into the chair, and as you can see in the thermal imaging, the model sitting on it mentioned it was like sitting on a piece of land warmed by the sun, which is kind of what it was. So in the remaining couple of minutes, I want to discuss 3 case studies of examinations for earth materials, keeping earth raw, making earth lightweight, and then making earth flexible. What does it mean to keep earth raw? So rammed earth is not a marginal technique anymore, but many examples, as you discussed, Paul, are stabilized with Portland cement, approximately between 3 to 7% Portland cement. And there are many reasons why stabilization might be good for rammed earth, for durability, for working with a material that is more wet. But given the thickness of rammed earth, there comes a question then about the absolute content of cement. 3 to 7% of a very thick wall might be the same as a very thin concrete section. So we call these in the natural building world rammed concrete or rammed clay concrete or dirty soil. And the question is, can we keep rammed earth raw? Is there a low-tech technology that we can use instead of the cement? And when I say low-tech, I mean a simple solution that performs in complex ways. And it's the work by Martin Rauch in Austria, who is highlighted in your book, that developed or reinterpreted the systems of lime checks. So instead of stabilizing, you create a check every 4 or 5 lifts using lime or stone plinth, and the lime check slows down water erosion and wind-driven rain. And with time, the exterior clay layer is eroded and the aggregate is exposed, creating a more texturized surface, therefore further slowing down erosion. So it's an exponential, mechanical, self-stabilizing mechanism, which we wanted to check. So we went to Lamont Doherty Earth Observatory and harvested soil from a nearby quarry, taking samples and testing the soils. And right at the entrance to the Geoscience Building, which is one of the research hubs to discover plate tectonics, this raw rammed earth was emerged with no cement. And it uses completely raw earth, rammed pneumatically and capped with a marine-grade wood, which is now a living laboratory for raw rammed earth erosion. And this is after 7 months, and it's doing fantastic. It's not melting as the scientists in the building were afraid of. The second case study about making Earth lightweight really relates to the multiple 3D printed Earth technologies that are emerging, and the WASP Tekla example in your book looked at these inspiring advancements. And at the lab, we asked ourselves, how can we expand mixed designs to rethink the weight, the thermal possibilities of 3D printed bio and geomaterials? And through an iterative process full of failures and successes, we are asking, how do we make this work also COD compliant? How do we develop a range of mixtures from lightweight to insulative to massive, easy to handle, to ship, and to comply with building codes? And this is one example of a piece we created from the light earth mixture we developed that is at the lab, so you can come and visit. It's hanging at the ceiling. And the third case study about making earth flexible was really started with an experimentation of earth as a wearable substance, creating earth skins that lended themselves to shape and sculptural form, or sculpture directly onto one's body. My dream is to be immersed with soil, with mud as much as possible. And we realized that wearable substances require flexibility. So we asked ourselves, how do we make soil flexible? How do we make a fabric made of earth? So we created different recipes using algae to create a mixed design comprised of 60% raw soil, sifted in a traditional technique used hundreds of years for pottery, to wear and be immersed with the soil through transcorporeal movement that affirms the agency of matter. We tested 3 processing techniques, essentially laser cutting, embroidering, and stitching, so using soil as a medium to perhaps heal the separated terrestrial perception of earth material. And I invite you to come to enter the lab's website, and it's right here in New York City, so if you're here, you're welcome to join, to visit. Thank you.
Good evening, everyone. Thank you for having me, and thank you to the wonderful presenters that have casted an exciting range of possibilities for biogenic and geogenic materials. Today, I'd like to talk about one of the forerunner feedstocks for biogenic building materials, i.e. biomass, materials that are made from living organisms, and specifically those made from plants. And more to the point around what are the greatest challenges and opportunities that I see with engaging with this wonderful resource. The sheer scale of biomass resources on the planet that we produce today is astounding. 4 years ago, we grew close to 10 billion tons of crops to feed ourselves. So this is the generation of resources that are intimately tied with our growth as a species. And if we include biomass grown for animal feed or biofuels, that amount doubles. And just to get a sense of what 10 billion tons of biomass is, picture 10 million blue whales. And if we think about the fact that today 40% of that resource is wasted between the farm and our plate, often it's degraded or combusted prematurely in open air, or lost somewhere between the farm gate and on what leaves our plates in our homes. This is astounding. With that scale in mind, one may argue that this is one of the world's most underutilized material streams and presents a tremendous opportunity to serve as a feedstock for a low-carbon built future. So the question that we always get asked is there enough of biomass to build with? And this answer is an overwhelming yes. However, when we begin to zoom in, the question also begins to illuminate another perplexing trend or pattern, which is which biomass streams are we scaling up? Over 50% of all the biomass that is grown on our planet today is one of the big four, whether that's sugar, corn, rice, or wheat. And so this question of diversity in biomass stocks is critical. Otherwise, we end up exacerbating or extending some of the intense impacts that we've seen that come along with monoculture farming. Historically, biogenic materials were used in very sophisticated ways in different climates, from insulative straw thatch roofs in the Scottish Highlands, hygroscopic bamboo roofs in Indonesia, aquatic reed that is used for enclosures in Peru. But today that is an incredibly limited range of crops that is being used in buildings. So large-scale monoculture farming that have large carbon footprints and drive decreasing biodiversity around the world is something we have to be very careful of not exacerbating. Over a decade ago, we started looking at other crops like coconut husk, which began to follow in the footsteps of superfood or super crops, becoming global marketing success stories which fuel demand, and observing what the underbelly of this economy is, which is the generation of large-scale surplus in context of production. In the case of the coconut, which is a lucrative food, oil, cosmetic product, it generates tons of husks along the equator around the world. And often the quality of this biomass resource is affected by the lack of proper waste management. For example, in Ghana, where I'm from, it is illegal to dump coconut husk in municipal waste streams due to its high bulk density and causes a lot of problem with machinery in landfills. So in addition to the biomass diversity challenge, there's also an issue of quality. And this is largely based on how we treat and view our waste. And something only stops becoming waste when we understand what it's made of and also understand its role in a broader ecosystem. On the other hand, I think the greatest opportunities that lie ahead of us is in how we are able to connect and integrate seemingly disconnected material life cycles, not only just to make effective use of biomass, but to extend how what we're doing affects the care of our broader ecology, particularly that of the land that grows our food, and a broadened set of actors that we're bringing to the table in terms of designing 21st century material life cycles. I'd like to talk about this opportunity in 3 quick verbs within a value framework for design. Firstly, for designers and architects, one of the greatest opportunities is for how we might be able to generate value and extend the lifetime of diverse biomass streams through the design of a range of building material products. How flexible can we engage these pathways of transformation from each agro byproduct and match them according to local or global demand? The second is also to think about how multi-crops instead of homogeneous crops might be used to generate a whole series of performances that we saw today: thermal, structural, acoustic, within new building technologies. How might our reacquaintance of the plant and the fungi world kingdom allow us to explore reducing embodied carbon in building material production? So understanding the relative amounts of cellulose might inform us to process it by feeding it to fungal materials that do very well with digesting cellulose to yield low carbon mycoproducts and low density mycoproducts. And stuff that contains more lignin be pressed into structural, more mechanically robust materials. So a quick clip of mycelium eating hemp over the course of 5 days. And how might these open up new sensory probiotic spaces where insulation is not hidden behind walls, but used to line the interiors of our interior spaces? The second and third opportunities are very much mid to long-term ones. The second lies in value translation and involves how we might collaborate with other actors, from farmers, new types of eco-manufacturers, building owners, and managers, to translate both existing forms of capital and generate new forms of value that is being brought to the table. We need to really think about how we make visible and reward actors for their participation in this emerging green collar economy, and how we might create new enterprises to facilitate access to biogenic building materials. This is sort of a map of one of our industrial partners, Ecovative, that began in upstate New York in Troy. And they've licensed this mycelium technology to a number of sites around the world that are sometimes housed in food production facilities, which interface with designers that can send their designs, and grow trays, which enable them to grow their products closer to sites of their consumer market. And this siting of production closer to the market is very much needed, given the fact that today's standards around materials and costs of producing might generate higher embodied carbon despite all these advantages that we've seen. And lastly, through all this, how might biogenic building material economies support the equitable distribution of value back to its generation and participatory systems? And while that's a much larger economic and political project, of course, shifting from this sort of centralized to distributed scale of production is critical, because ignoring this broader framework might make us complicit in reinforcing our dependency on extractive material paradigms. Thank you.
I'm so inspired. I have to say, I'm one of those material geeks. Talking about materials and the way our world is made and what our world is made from is like one of my favorite things to do. Thank you so much. I'm so inspired. And thank you to the League and to Paul, Mark, and David for producing this book, which gives us this opportunity. Just see. So in my 8 minutes, I'm representing my colleagues at the Health and Materials Lab and our obsession with this material hemp lime. In addition to being kind of inspired by materials, we are driven to bring materials to building that do not cause human bodies harm or any body's harm, any life harm, and also low carbon. So I'm just going to dive into this material that we've arrived at through the lens of reducing toxicity and reducing carbon, and we think it's kind of a superfood for the building economy. So it's the hemp plant and the limestone that brings these together. The hemp plant, as Paul described, is a plant that grows quickly, absorbs carbon from the atmosphere, grows in nutrient-poor soils, regenerates in the soil itself, requires very little water to grow, and doesn't need herbicides or pesticides, reducing toxicity. Limestone is an abundant stone that can absorb toxics and carbon from the atmosphere. And the hemp plant actually absorbs more carbon than trees. As it's growing, the hemp captures that carbon, but actually when it's dried and cut, that interior of the stalk is the part that we use for hemp lime. Limestone, on the other hand, is found in nature. It makes up about 8% of the Earth's crust. And it's found in geologies around the world. And it's been used for centuries globally. Here's an example of where the limestone is found in Denmark on the east coast at the edge of a sea. And when we look really closely, you can see in those cliff layers, there's evidence of fossil remains of animals like sea lizards and sharks and cuttlefish and tiny algae, which then are compressed over millions of years. This used to be covered in a sea 65 million years ago. And the debris creates this limestone, or chalk as we know it. Then when it's cooked in a hot oven, the limestone changes its molecular structure and becomes what we know as quicklime or calcium carbonate. That's then been, with a little bit of water, makes paints and plasters and mortars. Mixing that hemp with the lime becomes hemp lime. And as Paul said, it's also called hempcrete, but we don't like to call it that way because it has nothing to do with concrete, except maybe it's a little bit of an ingredient, but it's not structural by any means. It has all kinds of amazing qualities, hemp and lime. I was going to go through them. Paul listed them already. I think I'll just go very quickly. It's recyclable. You can use the waste to make new products. It thermally regulates in a wonderful way. It also regulates humidity and indoor climate, which is interesting because it makes a breathable wall or vapor permeable, meaning it makes places feel better. It absorbs humidity when there's abundant water in the air, and it releases humidity into dry spaces. It's also very effectively sound absorbent. When it hardens, it's like a stone, it's like limestone, so it makes it very hard for pests to get in there, and mold cannot grow. And it lasts for a long time. This is a bridge that was found, 600-year-old bridge that was found that uses hemp and lime mortar in its laying. It also absorbs carbon from the atmosphere for the lifetime of a building, not just in that one moment of building. So it makes for a carbon neutral or even carbon negative building. I think LTL covered this really greatly. We've done a deep dive into hemp lime for several years. And there's a few things I've just pulled to share with you that are really important to note. That hemp, even though it only became legal to grow in America in a couple of years ago in 2018, it's been grown here for thousands and thousands of years. Indigenous people have grown it and used it for all kinds of things for a long time, and the knowledge is still there. And also, in early American times, the hemp growing that happened was on the shoulders of enslaved people, and the knowledge of how to process hemp by hand disappeared with their know-how. And then in terms of the limestone, it's been used for centuries, again, all over the world, developed independently across continents before the internet, before anybody shared information. Each culture specifically had their own recipe for how to make usable lime plaster, paints, mortars. Now, laboratories are perfecting the limestone ingredients to be mixed with hurd from the hemp plant to make building materials. And in Europe, there's several companies casting hemp lime into panels and blocks. This is only now happening in North America. They're used for new buildings and also to renovate or restore old structures. So here comes to this project that we want to share with you, which is really, it's called the PA Hemp Home, the Pennsylvania Hemp Home, which began in 2020, and we just closed construction last summer. It's a collaboration built of several folks. Dawn Services is a small affordable housing provider in Newcastle, Pennsylvania, and they invited us to collaborate on the project because we share a vision, which is really to make that hemp lime buildings could make, and the whole system actually that makes hemp lime buildings, could make healthy, affordable housing and invigorate new economies for small towns, and maybe be an example for the rest of the country. Dawn Services works with local farmers and began growing hemp in 2019. They planted 14 acres, experimented with 2 seed varieties, and tested lots of planting methods. The Pennsylvania Department of Agriculture gave Don Services a grant to build this building, which is really interesting. There's the agricultural department and a building project to retrofit an existing home with hemp lime, which we believe is the lowest carbon intensive way, and also to conduct research and testing that will support the acceptance of hemp lime into the International Building Code. So here's the little house that was purchased by Don Services to be used as this prototype kind of retrofit. Of course, the existing materials in this house are mostly derived from petrochemicals, but when they're peeled off, what's exposed, of course, is the old wood. The initial idea was to fill the wall cavity, keep those wood studs in place, and fill that wall cavity with hemp lime, plaster it on the inside with lime plaster, stucco it on the outside, and make 3-layer wall. That was the idea, but things got really tricky during construction, and there needed to be a second layer of studs inside, and the contractor said, it's like building a house inside a house. And it took a long time. And the house, then, this is the house as it's being prepared to have hemp lime sprayed in it. This is the process. This is the mixing machine called the Mud Hog, and really it's just hemp, lime, and water. The valve on the right measures carefully just the right amount of water so that the hemp lime will retain its insulatory properties. It gets shoveled into this trough. This is all like very makeshift on site, and then pushed into a pneumatic tube, which is then, so the hemp lime is then blown into the wall cavity between those studs. And all of the scrap that doesn't make it into the wall gets put into these buckets, and then those buckets get poured back into the Mud Hog mixer. So it's completely recyclable. Here's the wall that's fully packed. It's kind of beautiful. As an insulation wall, and then bits on the outside were packed by hand. And here is the house fully blown. It took about 2.5 days, but had to dry a while, maybe 2 months, maybe even 3 months, I think, before the next stage. So the dry time is dependent on the local climate and weather. The plaster was made from hemp with a heavy dose of, it was lime with a heavy dose of hemp, actually. And there were a lot of issues in this in this mix. So like others have said, the mix is really important. And then the walls were finished with a finish coat of lime plaster to create a thoroughly breathable wall. And it's interesting to say that the lime plaster actually came from Pennsylvania also. Because the dry time was very slow, instead of using stucco on the outside, we had to use a rain screen, which my colleague Allison Mears brought out that solution. Well, why don't we just cover it with a rain screen and let it dry inside so that the construction could continue. So there was a lot of takeaways from this project, which were really interesting. One, of course, is this dry time, and it's a huge challenge for constructing in this way. But what we found during our research is that precast products are really the way to go. And so at Healthy Materials Lab, we have a good dose of ambition. We decided to produce our own kind of prototype, and we produced a bunch of hemp lime blocks here in the United States after seeing them produced in Europe. And the hope is that in the United States and in the future, there will be production facilities that do make these precast hemp lime products in large quantities, and ideally in regions near the farms. When we made this house, there wasn't an acceptable building code, which slowed the review time, of course. I was really excited to see that the PA Hemp Home actually is used as an example and in supporting documentation for the proposed hemp lime construction appendix for the IBC. And we acknowledge the many people on the U.S. Hemp Building Association who advocated for hemp lime, and now, this summer, it was announced that it will be an appendix for the 2024 International Residential Code, which is really exciting. At Healthy Materials Lab, we mapped the system that would need to be created to make this a viable industry in the United States. We visited farms in New York and in Pennsylvania and Kentucky and Italy to ask how can this industry be ignited for the future. Farming's gotten easier, but the equipment to harvest is still really a challenge. The plant is really tough and gummy. Talking with farmers, there's developments in hemp agriculture, but still challenges they face, finding the right seed, the right way to sow, the right way to harvest, ret, and bale the hemp. Decortication and processing is growing in the United States, but it has potential for growing much further. There are new industries that will support job creation, workforce development, but they're not yet thriving here in the US. The other facilities that will create job creation that are these facilities that produce hemp lime precast products. And there's an opportunity to reignite the masonry trades. And actually, we've been in touch with the International Masonry Institute, who's keenly interested in hemp lime. So you see that the hemp lime used on this product, actually, this PA hemp home was actually imported from France. And this is a problem. We need it to happen here. But we do believe that it can happen here, and it will, and it's on the way to grow. Yeah. So I'm excited for the conversation, and thanks for having me.
So we get the let's see here. We're gonna try to engage each other in a kind of conversation and then open it up to questions. I guess one of my initial questions, and I'll direct it to John Saras, just for you to elaborate on this question of how do we scale and how do we scale quickly, and what are the major impediments to that scaling? So, and then you were kind of hinting at local problems about the farmer, about decortication, about the need to kind of manufacture more hemp herd here. But what if you had the kind of magic wand that could change certain things? What are the major stumbling blocks to scaling the role of hemp in the U.S. at the moment?
Yeah. No, it's a great question, and I think it's happening, but it's happening slower than anybody thinks. I think the farming processes take a few years to understand how to grow any plant. I'm sure everybody agrees with that, and that is actually happening. But it's the supply and demand issue. It's a kind of a delicate balance. Like, we visited a farm in Kentucky, and they had farmed like 1,000 acres of hemp, and they had these beautiful bales, but nobody to process it. There wasn't a market to process it. So actually, there was a processor that was a startup that was like $2 million of investment. They started this decortication facility, and when they did it, they were too early and there was no hemp. So they shut down. And then the hemp came, and now there's no decortication. The machinery that's required to process, even harvest hemp, like a combine that's used for straw, for example, doesn't work on hemp because hemp is a very strong plant, and it's very gummy, and it gums up the machinery. So we need more equipment here. There's a lot of equipment in France and in the Netherlands, and folks are starting to import it here. But it's a process, and the decortication facilities too are, few and far between. They're starting to pop up. There was a new map that I just saw. There's like 2 machines in South Dakota, 1 machine, 5 machines in Texas. Like, everybody's looking for where those machines are. So, and then also, like, once you grow the hemp, then you need to, and there's decortication. Then it's important to get the herd the right size and to get it clean, because if you build with dirty or dusty hemp, it doesn't stick to the binder, and then it doesn't make a good insulation or a good wall. So there's all these levels. I mean, again, like, if we as designers are specifying it more, we're increasing the demand, then all of these things will move more quickly. But it's that delicate balance.
I also just want to add to that around the quality control of waste coming off the field. Our hemp industry, as you're saying, is incredibly young, and what tends to happen is, waste in some ways is distributed and it's relatively low quality. So those 2 factors mean that no matter what, the cost of producing a building material from dirty hemp waste is so much more expensive. And so we have, particularly when you go to the other spectrum of growing mycoproducts, you're feeding hemp to living technologies, they really care about what's in there. So if it's not clean, you get a ton of infections. And so it's almost cheaper to import that from the Netherlands than, spend all that money trying to clean agricultural waste here. So the more stakeholders that can get involved in that gap around processing good quality byproducts, maybe we have to get rid of the term waste, the better. Yeah.
And it all comes down to also the inherent variability in these materials, whether it's soil, geo, or biogenic materials. Natural materials are inherently extremely variable in their composition. Even within a construction site, one soil that you dig in one side will be very different from another soil that you dig maybe 10 feet away. And I want to say that perhaps as designers who can specify and help or increase demand, I'm also really excited about this conversation and about you being here, because designers also have an important role in developing products. You can see that with Biomason. You can see that with so many inspiring architectural products that are developed by designers and design researchers and material researchers. And there is really a strong need for, just so you know, for thin partitions, prefabricated partitions, finished materials in the US from biomaterials, hemp, lime, fiber materials, earth fiber materials. This is really, there's a strong need for that in the US. It is evolving, I feel, in Europe much more than in here. And we need more of that prefabricated kind of less than the in situ mode of product manufacturing, just because of the construction culture and trades that are existing at the moment.
Yeah, because, so Lolo, in a sense, what you're arguing, which I think is a key point, is that instead of thinking about materials that could be thought about as being connected to traditional building techniques, you're looking at basically moving to essentially architectural products as a way of not only bypassing the kind of one-to-one relationship between building with a material and a single project in order to scale, but also shifting the mindset of what one does as a designer, that you're not just designing the one-off, but you're actually designing the system and testing and researching and investigating the capacities of that system. To what extent is that then played out in your roles as educators in terms of how you focus on what one learns and what one teaches about? Because we tend to teach the seductive object that then happens to be built by this material, but flipping it so that you're focusing upon the design and invention and the social constructs that has to go around the articulation of a product, as opposed to purely the end piece as an end product. That was a question.
Yeah, I think that's a great question. I just developed a new course. It's an elective course. It's called Making with Earth, and I told my students something like this: I'm going to teach you everything that I know, and then you need to teach me something that I don't know. So I'm really opening up the lab for experimentation with students, 25 students in a small lab. We're working on it. But students have been so far producing a range of innovative, different mixed designs that I'm so excited about. From sargassum from creating alginate from sargassum to really pressing, printing, manually crafting earth, fibers, biopolymers that are naturally derived. So I think opening it up to creativity of students in an open-ended way is really important.
Yeah, and I know that, all of you are obviously involved in education in that way, and the idea that these ideas can now be transmitted to and further developed by a next generation of architecture students, designers, et cetera, seems like really critical to these things taking hold at a larger scale. The other question that's related to that would be not only, let's say, the education of people within the disciplines in the profession, but the other challenges related to not just like technical or regulatory impediments, but the perception of these materials within the kind of larger public, let's say. And so, for example, historically, earth has had negative associations in even a lot of the kind of cultures where it's traditionally used. Similar things for these other materials, agro-waste products. Even the word waste, right, kind of assumes a sort of kind of secondary character or quality to these materials. So I'm curious if anyone has thoughts about how we not only have to educate, of course, ourselves as architects and practitioners and builders, but also the people in the construction industry and in the larger kind of broader public to think about these materials in more positive, generative, and kind of optimistic ways.
Go ahead. I mean, maybe just tying in the education question to also the social engagement. I think in classes, I'm teaching a new seminar as well called Field to Building and Back, permutation on today's title, but how do we extend our historical understanding of biogenic materials and also evaluate with our tools today how those vernacular pieces of architecture perform, because there's a lot we haven't sufficiently understood about the performance traditionally. And also, I think what Lola was saying around, the hands-on experimentation is so key, because once we realize what actually goes into actually making and all the new forms of machinery and skills that one needs to develop, as well as a flexible mentality around performance, then that it might shift it away from just product, but to some fundamental understanding around material performance. What are the common denominators around these materials? Maybe the product actually isn't a building architectural product. Maybe it's the types of equipment that allow that to happen in a more democratic way. But also, I think it's a wonderful place when academia and community sort of a collaboration happen, because that really begins to challenge some of the ways we've perceived these materials. Biomass, like working with local agricultural waste in places like Ghana or the Philippines, is really challenging because these materials are going up against a developing context desire to modernize, so all the materials like glass, concrete, steel, and all of the interior comfort expectations that come along with those material paradigms are very difficult to shift. And so surrounding ourselves with concrete, glass, and knowing that a mechanical air conditioning system at the press of a button is going to condition, and we expect that, is very difficult to change back when we work with biogenic, geogenic materials that have a time lag and a very different way of conditioning. So readjusting that expectation through build prototypes, particularly at the one-to-one scale, has been a very important vehicle for beginning to change public perception.
Yeah, I think this is really important. I think, one of the ways that we start the conversation with students or with anybody, professionals that we talk about, is to ask the question, what's inside? What's it made of? What's any material made of? And, for the students, like if we start with polymers, any plastics, and you start seeing the list of ingredients that you can't pronounce that are making up our environments, basically, because the majority of our environments are made of plastic or polymer or polymeric materials, they get terrified pretty quickly to follow like the life cycle of a polymer is very different than following the life cycle of straw or hemp or cork, or like you all pointed out in your book, which and so like a few weeks into to a semester, the students are ready to use seaweed or biomass or mycelium and very excited to try that. But I think what the book points out so well is that in order for us to really change the dial, and we have until 2030 or something, this needs to be adopted fast and big. And it can't be a one-off situation anymore, which, is fun, but it's not good enough. And so I think, the opportunity for aesthetic convention is really important. Another thing that we think about a lot is materials aren't an aesthetic in themselves. Like you don't have to expose a hemp lime wall and look at or straw. It doesn't have to be an aesthetic of the farm. You don't have to live in the farm. You don't have to want to live in the farm. We could build cities out of this and, appeal to all kinds of walks of life and a lot of aesthetics. So I think, scale is the urgent question. And so that we take it out of this kind of one-off situation. And, and how do we do that? And so I think that the design of equipment is a really, I went to Belgium to ISO Hemp Factory to interview them. And it turns out the guy who started it was a robotics engineer. Yes, good start. Designed some equipment, but he designed a robotic equipment to make hemp line blocks. And there were no people like running, there was nobody like ramming those hemp line blocks. That was all robots. I wasn't allowed to take photographs, otherwise I would have shown you. But it was kind of remarkable because it's really bringing technology together with field, those biological materials.
I was just going to encourage questions. So if you have a question, I think there's microphones on both ends. Feel free to come down. We'll probably continue to talk, but if you have a question, please stand up to the mic and we'll let you ask that question. So you were going to say, Lola.
Maybe two things that also helped me with kind of bringing this into education or pedagogy are looking at the life cycles, but also at the material geographies, which is something I try to increasingly do to see where each material really comes from and through its life cycle of processing. And then the second thing is having, working with students to manage the procurement of materials in design build projects to actually know where they are sourcing the materials from the quarries, from the farms, etc. was also really, really insightful.
Please.
Thank you all for the presentation in this conversation. So my question is based in interdisciplinary collaboration. And as I was listening to you all talking about hemp and the need for the materials, I'm thinking like a team of engineers in the collaboration pool, as well as the farmers and the designers. Something just came to mind. Have any of you heard of any perhaps collaboration with the farmers, with this being 2023, and from a policy standpoint, there's like this farm bill where the farming community is configuring how they're going to be farming, and if they don't know that, hey, we can make a buck and collaborate with the architectural community and the design community to maybe collaborate and tap into some funding to drive that innovation. Has there been any talks about that?
I think that's the most exciting part of this, I think, right? I mean, that's what's so exciting about the PA Hemp Home is that it was funded by the Department of Agriculture, in Pennsylvania. And the guy who was in charge there, Mike, could see that connection. But I think it's, I think not everybody can see that connection. Like you say, oh yeah, the next buildings will be connected to the farmers that are, you go to any large contractor or large architecture firm, they're not going to actually see that link until we show it to them. So I think, events like this or books like the Manual of Biogenic House, I mean, I think this is what's going to be our agent, give us agency to have those conversations for sure. Weirdly, I think that actually the farmers are more likely to see the process or the connection more so than our side of the fence, more so than the designers or architects. Like I think that they, there's just a history of building with what's right there, I have a student right now who's doing a thesis on crofting from, the act of crofting in northern Scotland, which is just find what's right there, find what's in the field, find the stones, find the thatch, use what you have to build the next building. It's much more kind of intuitive way of building for people who live in rural communities than it is maybe for more urban situations. We've gotten so used to, what's on the shelf, what can we buy through the internet search?
And I'll just point out that there will be subsequent events to the series that bring together farmer, producer, designer, contractor, ideally to be able to really have that cross conversation, because it has to occur across that full cycle line. Otherwise, if there's a broken piece in that, the system doesn't work. In other words, it becomes a linear system if you don't have the full cycle. And it's not just a material cycle, but it's a human, social, economic cycle. It's a great question.
Yeah.
Hi. Oh, hello. Hello. Sorry about that.
Hi, thank you. I just wanted to thank each and every one of you all for presenting. It was a very riveting lecture to sit through. One of my questions has to do with economies of scale, because when you think about economies of scale, I think about, microchips, kind of the more you produce them, the kind of cheaper they get, or vaccines, things like that. And oftentimes when you think about economies of scale, you're thinking about how to streamline efficiency. And I'm curious if you guys think of, you were talking about variability and the presence of variability in kind of biogenetic material. And I wanted to know if you all believe that variability is inherently inversely proportional to efficiency, or what are the benefits of having a variability as from a design perspective, from a structural perspective, from an economic perspective, because it's often seen as a liability.
Yeah, that's a really good question, Jenna. Jenna was a researcher at my lab. Well, it really depends on design and building culture, right? And how we perceive materials as either clean, sleek, precise, cold or warm, messy, porous, disobedient. So depending on this perception will dictate material demand or product supply chain, etc. And the inherent variability can be therefore seen as either a quote unquote good thing or a bad thing, right? It really is something that I would say is driven by design and also by perhaps technocratic material engineering and sciences that try to engineer materials to create artificial materials, to synthesize and create the most granular characterization of material. So you look at sand. Sand in the concrete industry uses Ottawa sand because it's highly refined grains of sand, which is for construction, it's not the ideal sand. It's angular, it's not, it's round, it's not angular and jagged, so you don't want to use it, for instance, in earth construction that uses clay as a binder, and you need that surface to bind the material. You want that high variability of particle size in earth construction. So there's something about natural materials that asks for that inherent variability. I'm not sure in fibers, but I'm assuming that when we're talking about lignin versus cellulose and the composition of a fiber, there are also ranges and changes, and how do we account for that?
Yeah, I think that's such a great question. And if you asked me that 8 years ago, I have no idea it's a problem. And rather, I think, I've tried to sort of see these problems as opportunities. How does this become a value add? And I think, it really depends. So for example, hierarchy is important when we think of variability. Where can you not compromise on performance? Structural, mechanical, and where can you? Infill, insulation, all of that stuff. And you might have a technology like fungal technologies, mycelium, that are very good at digesting a whole series of substrates, agrofiber-based substrates, and generate a relatively homogeneous product, and you still can increase its performance by pressing. So there are actions or operations that can happen to further standardize or achieve a certain amount of predictability in performance. And I also think, we love variability aesthetically, visually. And I think about that a lot, particularly in terms of customization, coding, and how we might celebrate multi-cropping practices through that customization. Because often green gets you in the door, low carbon gets you in the door, and the thing that truly sells is customization most of the time when you're trying to sell an architectural product. So for example, we have this wonderful research project supported by the Western Foundation Research Prize looking at bio-based dyes and really sourcing dyes based on indigenous farming practices that are based in multi-crop diversity. And the generation of spectrum of color, tactility, are things that are all expanding customization options and not huge differences in processing, to achieve that. So I think that's probably where our value, can really go through the roof. Layering is another wonderful example of, keeping the low density stuff inside and the more structurally robust fibers on the outside to deal with abrasion and all of your mechanical loads. And that sort of Kit-Kat layering methodology is just another way of accepting variability without compromising standardized performance.
Over here.
Do you think there's likelihood to create mobile decortification and systems that, like, bring the circus to town and everybody get their hemp or whatever it is processed together? Do you think
They
that's-
exist.
It does exist.
Yeah. It's called the mini decorticator with wheels. Yes.
So,
But that's the idea, right? And this, it should be local. It should be local, and they're expensive machines, so it makes a whole lot of sense to,
I'm glad to hear that.
Yeah, no, that's exactly it. And in terms of the last question too, like, how do we understand variability? The ideal situation is to get the original ingredients from, a very local area and be able to process it right there and make it right there. Similar to like a concrete block. Manufacturing is local to a region because it doesn't make sense to truck it across the country or ship it across the world. It's a similar, yes, exactly.
Yes.
Hi, I'm Sonam. I am actually starting a venture studio to build climate solutions for cities, and I actually have a background in policy. And, in New York, we have One NYC, right, our climate plan, and so much sort of written knowledge about what the aims of the city are. And that process is replicated in cities around the world. What we do is, if you could wave a magic wand and actually implement One NYC, what products and services would you want, right, as a city government? And Lola, you mentioned that, you sort of gave your laundry list of products that you wish existed in this space, and particularly in the United States. But all of you also mentioned companies that have done this really successfully in Europe, right, or in other parts of the world. And I'm just curious to hear of some of those examples of those companies, and then also what are things that could be improved as some of that knowledge comes over to the States and as we build this industry here?
Yeah, I can talk a little bit about, so I had the pleasure of going to Denmark and looking at what products are available. If I could go and, just source products that are made from seagrass or from hemp or from other forms of clay boards, for example. These products just don't exist here, but they do exist, and they exist in other regions of the world. And I think one of the real questions put forward to the design community is to start demanding these, and also from the standpoint of material invention. I was arguing to some of my students that if I was coming out of school, I would look into an entrepreneurial spirit to make a company that produces these materials, because there will be demand, there needs to be demand, or maybe we're highly optimistic there will be demand. But it is these kind of cycles, and I think to be able to not have to import the materials, but have them locally, and if we look to CLT as a kind of poster child of transformations that have occurred, are there ways that we could have similar transformation in the role of straw-based products, hemp-based products, cork-based products, clay-based products, et cetera, as well as having architects and designers think about how they might invent those very materials within their own designs themselves, so it's not just product specification, it's the full range of those things. But to also piggyback on the question of policy, there is a social cost of carbon. And if there is a quantifiable amount attributed to carbon, then all of a sudden the market changes. So instead of having it being something that's desired, it's actually something that's bottom lined. And I think that policy change is fundamental to be able to deal with questions of scale. That the moment there's a cost for building that is attributed to its carbon and to its health issues and to the chemicals produced. Once that's costed and not pushed onto a future to deal with, because the future is now present, then you change the way in which the economics work, that the market for something all of a sudden isn't unusual, outlandish, the one-off. It's actually now the most economic, the most affordable, and the most desirable. I think over here.
Hi. So I want to go back to the idea of scale. And Lola, you were talking about how as we want to kind of encourage adoption of these materials, we need to start thinking of them more as architectural products rather than specific site-specific one-off solutions. And while that sounds like an essential step towards kind of like mass adoption of these kinds of technologies, I also worry that perhaps as you start to think of a product and conceive of it in those terms, a whole different logic of perhaps marketing and sales and profit on the product side of things can perhaps threaten to detract from the benefits that currently come along with these kinds of materials. And I'm thinking about a recent discussion we had at school about biofuels and how some legislation that was introduced here in 2007 kind of led to the creation of this whole palm industry in Indonesia and the disaster that was environmentally, and how that kind of overrode any of the environmental benefits that would have accrued from a local industry. And so I wonder, as you scale up and start to transition to this kind of more generalized product-based conception of these materials, how do you avoid that kind of set of unintended consequences? And then also, where does the agency of the architect lie? And I wonder whether, like, in addition to specifying materials, we also need to start thinking about specifying their provenance, or I don't know.
That's a great question. There's something really unique about natural materials that you find them where you need them. Very generally speaking, you'll find insulation, natural materials, fibers, where you need it for colder climates. There will be an abundance of clay-rich soil, perhaps in more arid areas or warm areas. So there's an inherent locality of natural materials. And I think that when I think about product development, it does not necessarily imply upscaling, monocropping, and in ways that create a problematic, sustainable Home Depot kind of situation where then we need to think about product development in natural materials, earth, biogenic, geogenic materials, the way we think about permaculture, the way we think about local production, distribution lines, circular economies, etc. So it's not necessarily a material production streamline that is takes place in one location and distributes to all. So it's inherently self-organized, the distributed system that needs to happen, of course.
You know, I think this is the paradox that I've been kind of mulling over in my own mind as these conversations are ongoing, which is that what's like fantastic about a material like earth is that you can derive that material from the site in which you're building it, right? Often from the excavations, say, for foundations or things like that. And so there's an inherent relationship between the material construction and the kind of locality and the site. And the scaling up to kind of what we would maybe think of as kind of mass production of building materials, kind of modularized, standardized building materials in the conventional sense, immediately kind of, or at least potentially disengages the relationship, right, between the kind of local resource and its implementation on site in situ, which is what is, you know, so kind of engaging about a lot of these projects. And so it is a really good question and an interesting kind of paradox. How do you, on the one hand, take advantage of the kind of necessary standardization, the kind of predictability that products allow, while at the same time not kind of overstepping or somehow losing these kinds of really kind of rich potentials of the material as it's kind of connected to specific regions, localities. And I'm reminded, Mei Ling, of your comment about maybe we don't need standardized materials as much as we need standardized practices or processes or kind of mechanisms, right, that can allow for these things to kind of take place in a more predictable way while still allowing for imagination and invention.
I will say that one of the really nice things about this panel is that the questions are emerging. There's a lot of other questions that are possible, and the conversations will continue. This is the first of a series of programs, really trying to engage what is a really fundamental shift to how we think about architecture, how we define architecture, how we think about our relationship with the earth, and how we can invent ways to imagine different and more beneficial processes. But I'm going to have to shift us to kind of wrapping up conversations amongst ourselves and encourage you all to come back on March 15th for a conversation about stone, and in particular structural stone as a way of rethinking how one could use this, incredibly seemingly well-known material, but in new ways relative to the problems of concrete. So, and then stay tuned for other programs that will be announced. I won't put a date on it. Announced soon, related to this program. But thank you all for coming. Really appreciate your presence.